Okay, guys, this is the last topic for the course. It's been a long time coming, but this is it. And this, I think, is one of the more complex topics because it requires a lot of what we did throughout the course. It's a good summation topic. It's chapter 14 in your textbook, shear stresses in beams. Okay, these are the background notes, about 4 pages. I'm going to talk through them. Then I'm going to give a video of 2 to 3 class examples. They're pretty lengthy. And then we'll assign homework, and that'll be it right before test 4, and then the cumulative final exam. So let's finish strong, okay? Okay, so chapter 14, these are the highlights from your textbook. Okay, so for a beam to be safe to carry a given load, it must satisfy design stress limits for both bending and shear stresses. In most cases, bending stresses are the more critical and the higher ones, but shear must always be checked. There are some situations where shearing stresses are the predominant mode of failure. For example, in wooden beams, thin-walled beams, short beams, and laminate beams. For steel, I-beams, members, not so much the case, but we want to be robust in our studies. We want to take care of all of it. Okay, so of course, stiffness or resistance to deflection is also an important goal when designing a beam. This course runs out of time, doesn't go into the deflection of beams, but there are whole field of study on that as well. So I'm going to use some figures here just to prove a point. So figure 1 basically is on the second page. If a small stress element subjected to shearing stress is isolated, we can see that it must also have a horizontal shearing force to keep it in equilibrium. Otherwise, the element would be skewed. So if you have something trying to make something a square into, say, like a parallelogram, right? There has to be something pushing back to keep it from doing that. And as we did before, most of these equations and all the things we've studied come from calculus and derivations, where they take a small volume of material and they do an analysis on that small volume and then blow it up accordingly and do some analysis. So on every small little section of a beam that may be loaded, there are little internal reactions to forces, and those are the shear stresses, okay? Figure 2 is the illustration of the presence of shearing stresses in beams. A good way to see it is this figure here. If you had strips loosely stacked and you put some bending on them, you would see they would actually start coming apart there. If you staple them together, less so much, and if you glued them together or you laminate them, they would act as a more homogeneous part. But that just goes to show that within the beam itself, the slices of it are trying to get away from one another, right? And the shear failure, we talk about grain direction wood, figure 3, the shear failure is likely to occur along the lines of grain. Remember, this is the way that the tree is actually, this is the way the tree is actually grown, right? Here's the rings, you can see them concentrically here. Right, so this is the top view. This is how the tree would be standing straight up, and that's how they fare. So each ring is another year of growth, right? The grain of the wood, that's another year of growth. Every time the tree gets a year older, it gets another ring, and that's how the wood would delaminate. Okay, page 3. Now let's get to the mathematics part of it. Okay, now this is a fairly complex explanation, but I'll go through it the best I can. The general formula, which can compute the magnitude of shearing stresses at any point within the cross-section of a beam carrying a vertical shearing force, is tau is equal to VQ over IT. V is the shearing force at the cross-section of interest. It'll be the first graph in our shear moment diagrams, where we've been picking off the bending moment value for the bending stress calculation, sigma equals MC over I. Well, here we're going to pick off the highest V value, or a V value at a point of interest. And that's why we do a shear moment diagram, because we're going to use that here. I is the moment of inertia of the entire beam's cross-section. You're familiar with that. Thickness is the beam's cross-section where the shear is calculated, so wherever you want to know it, that's that T. It's different than, it's similar, I guess, to C in MC over I, but it's not the same. And Q is the most complex in all this. It's the first moment of area at respect, excuse me, and here's a mouthful, right? Try to take it in small pieces. It's the first moment of area with respect to the overall centroidal axis, right, of the area of the cross-section that lies away from the axis where the shear stress is to be calculated. Basically, what that means, and I made a little figure here, right? So Q is a value, and it's going to be the AAP, which is the area of the part that the cross-section lies away from the axis where the shear stress is to be calculated, and Y is the distance of the centroid of that area to the entire beam's centroidal axis, okay? Basically, here's a little sheet I made up. This is an I-beam, right? And we're going to find in a second that unlike bending stress, the shear stress is maximum at the centroidal axis, or the neutral axis. Bending stress is the opposite. Bending stress is 0 here, and as it gets further away from the beam, the bending stress is maximum here and here. In shear stress, it's exactly the opposite. Shear stress is negative away from the beam and maximum at the neutral axis. So if I wanted to find the maximum shear stress in this cross section, I naturally would want to find it along the centroidal axis. But what if I wanted to find the maximum shear stress here, or here, or here, right? Anywhere in the beam, or here. Basically, wherever you want to find the shear stress, right? If I wanted to find the shear stress right through here, it would be just like blotting all the rest out. Now this is my area that's left, this whole thing, this two-piece area. Where is the centroid of this whole area? It's probably somewhere over here, right? Q is A times P, is AP times Y. AP is all the cumulative area, and Y would be the distance from here to the main centroid of the beam, would be this whole distance. What if I wanted to find the shear stress there, right? Pretty easy. Q would be this area, this entire area, and the centroid would now be there. That Y bar distance would be from here to the centroid of the beam. So depending on where you want to find the Q, kind of visualize it with this, right? So when we're trying to find the shear, that Q value is wherever you want to find it, cover up the rest of the beam. And sometimes it's a one-piece area. Sometimes it's a two-piece area, right? And basically it's just a multiplication of that P times Y. So once again, say I wanted to find the shear stress right here, okay? Cover that up. AP is this whole thing, the area, okay? And the centroid of this new region is there. The distance between here and the overall centroid, that's Y bar. So that's my Q value, okay? Last page of the background theory. Q has units in terms of length to the third, either inches cubed, meters cubed, millimeters cubed, what have you. And obviously we saw in the last little visual that sometimes the area AP can be made of several different composite areas. You know, if you wanted to find the shear stress here, there's one area, but if you wanted to find the shear stress here, you have this whole area plus this whole area. So now you've got a composite area problem. If that's the case, if the AP itself is now a composite area made up of several component parts, this is what you should do. Divide AP into component parts, label them A1, A2, A3, etc., and compute their original area values. Number 2, locate the centroid of each of those component areas. And 3, determine the distances from the centroidal axis, the main axis, right, of the full section to the centroid of each of those components, calling them Y1, Y2, Y3, etc. So, and then 4, compute the calculation for Q is AP times Y bar, okay? So, that's my dog crying, I'm sorry about that. So this is if you have a large component area, many components, say you have a 3-component area that you have to find Q for, this would be A1 times that Y distance 1, A2 times that Y distance 2, and actually these should have bars over them, okay? Okay, so that's basically how we're going to do the calculation. I'm going to illustrate that in a couple of examples, and you'll see it. It's going to look a lot like the moment of inertia questions where we make a chart and we do a lot of multiplying and find the centroid, et cetera, et cetera. This time we take it one extra step. And here's, if you did a plot, we talked about bending stress. This is an I-beam looking sideways. Here's the top flange of an I-beam, the top flange of an I-beam, the bottom flange of an I-beam. Notice if you plotted the bending stress in the neutral axis right here, there would be 0 bending stress and its maximum as you get to the end. Shear stress looks totally different. It's actually maximum at the neutral axis and 0 at the outermost fibers. So in theory, any cross section, if you wanted to find the maximum shear value, shear stress in any beam's cross section, you would always look at the neutral axis. There may be a point of interest somewhere else in the beam's cross section, maybe where the flange and the web meet. But predominantly the max shear stress is going to be found here, and back before we are, the maximum bending stress is found depending on which way the beam is bent, compression or tension, but the values should be similar, okay? That's the end of the background theory. The next couple of videos, 2 or 3, will be on examples. Okay, thanks.